today's presenter name is Zhijun, and he's a PhD candidate at China University of Petroleum under the supervisor of Dr. Shaji Song, and will defend his PhD in June 2024. He has published 5 journal papers and authorized 3 patents for his PhD work. He also published 5 journals. He's also a youth editorial member of Xinjiang Petroleum and Natural Gas Journal. He spent his last year at the University of Alberta under the supervision of Dr. Bo Zhang, and continued his research on his artificial intelligence technology techniques to achieve reliable prediction and optimization of the drilling efficiency and cost for subsurface energy development. So his presentation is about the intelligent optimization of drilling efficient based on prior physical knowledge. And I'll just say, do you want to go through the abstract yourself, or do you want me to just talk briefly about it? Okay, I'll just go through it briefly. So the drilling engineering is an engineering process that uses mechanical equipment to break formation rocks and form communications with subsurface resources. However, the high cost of drilling directly affects the large-scale development and utilization of underground resources, such as petroleum, geothermal, and CO2 storage in deep formations. Increasing the drilling efficiency can effectively reduce drilling costs, solving the outstanding issues in the uneconomical cost of geothermal and CO2 storage in deep formations. In recent years, the development of artificial intelligence technology has set off the 4th industrial revolution. And intelligent drilling technology has also emerged, which is also considered a transformative technology that can significantly reduce drilling cost. However, the accuracy, stability, and mobility of fully data-driven artificial intelligence models are difficult to meet the requirements of field application. Therefore, exploring a reliable and accurate drilling optimization method that combines prior physical knowledge with artificial intelligence technology has become the key to intelligent drilling technology. In this study on our intelligent rate of penetration, ROP, prediction model embedded with prior mechanism knowledge was established from physical boundary conditions, neural network structure, and control equations. And the established proxy models were analyzed and explained through interpretable method. Based on multimodal graph learning, multiple individuals drilling agents are fused to achieve a more accurate representation of the drilling environment under limited data conditions. Use intelligent optimization algorithm to achieve multi-objective collaborative optimization of drilling parameters and automatically generate and optimize the drilling scheme. So applause to the presenter today, PhD candidate, Zhijun.
Okay. Good afternoon. My name is Zhijun from China University of Petroleum, Beijing. Today, my report topic is intelligent optimization of drilling efficiency based on prior physical knowledge. My report is divided into the following 6 parts. As the audience of this seminar may come from different majors, please allow me to briefly introduce the basic concept of drilling engineering. Zhijun is a project that uses mechanical equipment to break formation rocks and form circular holes of a certain depth, and thereby establish a connection channel between surface and
sorry, it's not moving to the next slide. It's not moving.
Oh. We're having some technical difficulties. Yeah, I'm gonna close the file again and see. Yeah, let's try to open it. That's weird. So.
okay.
Yeah, that's
It's fine.
Okay. Drilling is a project that uses mechanical equipment to break formation rocks and form circular holes of a certain depth, and thereby establish a connecting channel between surface and underground resources. This is another shape of horizontal well, and drilling engineering includes multiple sub-processes such as rock cutting migration, pressure control, and so on, involving knowledge from multiple disciplines. Such as geomechanics, hydromechanics, material mechanics, chemistry, and so on. Drilling engineering technology is also widely used in many engineering fields, such as geothermal, resource utilization, carbon dioxide storage, and nuclear waste storage. However, the high drilling costs and constrain the large-scale economic development and utilization of these underground resources. In recent years, with the continued advancement of the digitization and automation of transformation of the engineering industry, the AI technology based on big data developed rapidly. By using AI technology, some simple tasks that require human participation can be replaced. And AI technology also have the advantage of high efficiency and low cost. AI has been successfully applied in many engineering fields, such as the image recognition, AI driving, AI translation, and AI medical care. Successful cases all provide the benchmark for other industrial fields. The AI technology also brought a new opportunity to the development of the drilling technology, and the drilling and the intelligent drilling technology also emerged. Intelligent drilling technology is based on the interdisciplinary subjects such as big data, AI, Internet of Things, control engineering, cloud computing. It achieves comprehensive perception, autonomous combination, and intelligent decision-making of strata, variables, and ground condition through the organic combination of the drilling equipment, downhole tools, and the intelligent system. Intelligent technology covers all processes in the drilling field, such as the advanced formation detection, variable precision guidance, and parallel closed-loop control, and intelligent decision-making. Drilling efficiency as the last loop of the intelligent drilling have the high have intuitive and important research significance. My research is focused on the intelligent optimization of the drilling efficiency. The intelligent optimization of drilling efficiency is achieved through the collaborative drilling multiple system, real-time monitoring and creating the drilling state, and then to achieve the intelligent optimization and recommendation of the drilling parameters. The drilling theta is referred to the formation property, variable stability, rock breaking state, and string state. Among them, the ROP is the most intuitive intuitive expression of drilling efficiency, and it also have the extremely high research significance. Next, I would like to conduct the current state and challenge of intelligent drilling, intelligent optimization of drilling. The conventional drilling optimization method is based on some assumptions using experiment, numerical simulation, and a statistical equation to simulate the drilling process, and optimizing the drilling parameters through the optimization method. Due to the complexity and the limitation, the conventional method only can analyze a few parameters impact on drilling efficiency. In addition, the economic and the time costs of indoor experiments and the numerical simulation are high, making it difficult to meet the requirement for the real-time drilling optimization. But AI method do not require make any assumptions, and the AI algorithm can fully explore the association information between multiple drilling parameters and target. Once the AI model is trained, real-time prediction and analysis can be achieved. Compared to the conventional method, the intelligent method have the advantage of high accuracy and high timeliness, which is crucial for the drilling operation. However, the migration stability and stability of the pure data-driven model are poor, making it difficult to meet the requirement of the high cost and high risk drilling operations. This is also the main challenge faced by the current intelligent drilling model. Based on my research and analysis, research on the intelligent drilling model still need to be strengthened into the following four. I think the following four aspects. The first one is the knowledge embedding. The second is the interpretable analysis of the AI model. The third one is the couple research on multiple drilling agents. And the last one is the multi-objective collaborative optimization. First, I would like to introduce the drilling data I use in my research. The drilling data we use come from 23 deep wells in the Petroleum oil field in China, with an average depth of 6,020 meters. Among them, PW1 is in the central of block 2, and PW2 is at the edge at the block of the edge. These two wells are about 25 kilometers away. A total of 8 formations are encountered during the drilling. And after we analyze the average ROP of this 8 formation, we found that in block for block 2, the N1J formation and the formation below 6,000 meters are the ROP, low ROP areas. Due to the lack of the drilling data in the deep formations, my research mainly focused on the N1J low ROP formations. We also made a study of the lithology of the N1J and the E23S formations. From this picture, we can see that the difference between N1J formation of well PW1 and the 23 adjacent well is minimal, while the E23S formation is biggest as this one. This one is the formation statistic of the 23 adjacent well. Based on the acquired drilling log and logging date, a total of 5 types of drilling parameters were selected. I called it geological, trajectory, and engineering, drilling flat, and drilling beta parameters. From this lot of parameters, we finally select 16 parameters, like this one, like the gamma ray, acoustic, and so on. Due to the human interference and mechanical vibration, there are some abnormal points and noise in the raw drilling data. We use the full touch rate ring and the threshold method to remove the abnormal data, and use the fast Fourier transform method to remove the noise. These two figures show the comparison of the training data after outlier processing and noisy reduction. It can be clearly seen that the outlier are removed and the noisy update is greatly reduced. By analyzing the correlation between training parameters and OP, the optimal parameter can be filtered as the input of the model, which is greatly helpful in reducing the complexity of the OP predicting model and improving the calculation efficiency. The upper right corner of this figure shows the Spearman correlation coefficient, and the lower left corner of this figure shows the correlation coefficient of the mutual information. We can see from the figure that the absolute value of Spearman correlation coefficient between OP and most training features is less than 0.5, and the NEMI coefficient is of most training features with OP are greater than 0.4. We can draw the conclusion that the linear correlation between OP and most training parameters is weak, and there are a strong nonlinear correlation between OP and most training features. Okay, next I will introduce the model I struck like the WDC model for the OP prediction. At first, when we analyzing a problem, we should first should know the relationship between the parameters and the target. It need to be analyzed from two aspects. The first one is the univariate correlation, and the second one is the multivariate correlation. Univariate correlation analysis treats other variable as constant and analyzes the impact of a certain parameter on the target separately. Multivariate correlation analysis considers the interaction between the multiple parameters. This equation is the modified Young's OP equation, which is also the most widely used OP equation. We can analyze the multi-training parameters, the relationship between multi-training parameters and OP from this equation. We can analyze the correlation relation between the multiple training parameters through the derivative equation, like the partial OP to a partial WB. From the univariate correlation analysis, the weight on beta and the OP are linearly related, while the other parameters are non-linearly related. For multi-variable correlation analysis, there is a cross-multiplication relationship between multiple training parameters. We all know that deep fully connected neural networks are known for their powerful nonlinear fitting ability. Although DNA model performed well in most application scenarios, but there are still a lot of people still trying to improve DNA's performance and propose some new network structure like the WDL model and the DCA model. According to the research by Google and Stanford University, adding the linear network and cross network can further enhance the linear fitting ability and the cross multiplication fitting ability of the neural network. Based on the modified Young's equation, we know that there are linear, nonlinear, and cross multiplication relationship exists between the reading multi-parameters and the OP. And the existing DN, WDL, and DCA model all cannot fully capture the complex relation between the multi-training parameter and the OP. Therefore, the WDC model is innovatively proposed in my study. That the WDC model is mainly composed of this the linear network deep layer and the cross layer to fitting the linear, nonlinear, and cross multiplication relationship. The network structure of WDC model is shown in this picture. We input a linear correlation parameter into the linear network and the nonlinear correlation parameter into the DNN model. and then use the output of the wide model and deep network to the cross network. Finally, the output of these three networks are input to the output layer of the double descent model to get the final LP. This double descent structure is obtained by analyzing the principle of LP prediction. But I think, of course, if there is such a relationship between multiple parameters and targets in other engineering field, I believe that the double descent model will still show its superiority. In the engineering field, application is not only required that establish the LP prediction model has high accuracy, but also has high mobility. This study evaluates the established intelligent LP model from 4 cases. The training and validation data set of the 4 cases are all generated from 23 adjacent wells in the JDK formation. The text data set of the case 1 and case 2 are data from the JDK formation of the PW1 and PW2 well, respectively. We're trying to use this to evaluate the model's migration ability on the same formation in a new well. While the case 3 and case 4, the text data set of case 3 and case 4 is the SUI formation of PW1 and PW2. We're trying to use this to test the migration ability on the similar information of a new well. This picture shows the performance of the BY of the LP prediction model, like the BY model, D model, WDL model, DCM model, and WDCM models. And we can see from the picture that the performance of the BY, the conventional BY mechanical BY equation model is the worst, and while the WDCM model performed the best. In the result of 4 cases are shown in these four figures. On case 4, the accuracy of all LP predicting model has significantly decreased. You can see from this, with the MRE of BY model equation increasing at most at about 31.64%. The increasing in WDC model was the least, about 18%. On case 1, the accuracy of all models decreased at the least, while the MRE of BY equation increased the most, about 15%, while the WDC model increased at least at about 7%. We can see that when the data similarity is higher, the accuracy decreases less. On the contrary, the data difference is greater, the accuracy decreases more. Overall, the WDC model has the smallest decrease in accuracy and exhibit the higher mobility. The next patent is the interpretability issue on intelligent model, which is also the hot topic and difficult in the current AI research. We all know that the deep neural network model is a black box model, and its interpretability is mainly caused by the calculation about the hidden layer. We take a neuron in the hidden layer as an example to analyze the uninterpretable of the DNA. The calculation of a neuron in the hidden layer is mainly divided into the 2 parts. The first one is a linear combination. The second is the activator calculation. Apparently, the linear combination is explainable, but the activation calculation is unexplainable. If we can make this part, we can explain this part, then we can. It's good for the neural the network is interpretable. In my study, I transformed the operation of the active calculation into an interpretable substitution, and we can achieve the interpretable DNA. For the ReLU activation function, we discover a very interesting rules, as shown in this formula, where DR is the derivation function of ReLU. Based on such a convention, we can convert the function operation of the ReLU into a matrix operation. After simplification, we find that the output of the DNA model is a linear combination of the input parameter. However, unlike the conventional linear combination, the weight parameter and the bias of the linear combining are constantly changing. The weight parameter is a correlation to the input parameters like DR, and this is the second layer of DR. This is the third layer, and this is a layer of DR. The DR matrix is composed of 1 and 2. We can consider that the one in the DR matrix can be regarded as a neuron being in the activated state, while the 0 is in the inactivated state. In order to avoid the interference caused by the training date difference, we use the data of 3 adjacent wells to establish the RP prediction model. We established the RP model with different activity functions like this picture. We can see that the RP value, the RP prediction model with value activation function perform the best, and the 2 figures show the MRE and error distribution of RP model. We can see that the established RP prediction model performed both well in the 2 different formations, and then the impact of the formation difference on this model can be ignored. As the number of the training epochs increases, we all know that as the number of training epochs increases, the accuracy of RP model will continue to improve like this. I got the table of about 5, 10, 15, and 20% MRE models performance. If we with the increase of the epochs, the RP model will gradually change from the under fitting to forfeiting, and then to the forfeiting to the overfitting. We made the statistics on the activation state of the neuron on each hidden layer. This figure shows the relative activation frequency curves of the 4 hidden layers. It can be seen that as the accuracy increases, the relative activation curve of neurons gradually moves closer to that of the 10% MRE, like the red curve. When the MRE is 5%, the blue one, the relative activation curve changed greatly. So far, we do not know why this thing will happen, but we suspect that when the model MRE is 10%, the model is in the fully fitting state, and when the model MRE is 5%, the model is in an overfitting state. The further evidence will be given later. As shown in the 2 figures, we can take the activation frequency of the neurons. When the MRE is 5%, the activation frequency of neurons is concentrated in a certain interval. In hidden layer 2, we can see that the most neurons activating frequency is lower than 0.3, and when the MRE is 10%, the activation frequency distribution of neurons is relatively uniform. Concentrated distribution indicated that a large number of neurons are in a fully activated or completely inactivated state, which is not conducive to mining the hidden information of the training data. The uniform distribution represents that the model are not only mining the micro features in the training data, but also mining the local features. In addition, we also found that the some data a small set of data activation frequency curve are it's a Z shape like this. We can see it's like the letter Z. We call the number of neurons that are either fully activated or not activated the transition length, like from this to this length. We call it the transition length. Obviously, when the data is completely same, the transition length will be 0. This set of data shown in this table. We can see from the standard deviation and the mean value of this data that the difference in this set of dream data is very small. We can also call this set of data the similar data. The next is the weight parameter interpretation. Since the training parameter is standard when we input, in order to obtain the true weight of the training features, the weight parameter must be reversely transformed, like this, like we use these two equations to reversely transform. And this table shows the information of the weight that after reverse transformation. For the convenience to analysis, we take the change in the weight of WB and the rotary speed as an example. We can see from these two figures. Similar to the activation frequency curve of a neuron, as the accuracy increases, the weight curve gradually move closer to that of 10%. As the right one, 10% MRE, and when the MRE is 5%, the weight curve changes greatly. It's the blue one. On the other hand, when the MRE is 5%, the weight change trend is closer to that when the MRE is 20%. On the other hand, the weight when the MRE is 5% is value some physical laws. In drilling, the weight on beta have a positive correlation with RP, but we can see from the picture some weight is lower than 1, so it's violate some physical laws. So we can verify that we get the following conclusion: when the model MRE is 10%, the model is fully fitting a state, and when the MRE is 5%, the model is in an overfitting state. If we take out the weight parameter of the similar data and average them and average them, we can establish a corresponding linear substitution equation like this, like this equation. Using this linear substitution equation, we can intuitively get how the RP intelligent prediction model works in this interval. By analyzing the weight, we can quantitatively analyze the impact of training features on RP, whether it conforms the physical mechanism, and whether the model is trustworthy. In addition, we can also establish an RP increasing equation like this, based on the substitution equation. From this equation, in order to, we can see that in order to increase the RP, we should to increase the RB, WOB, and the rotary speed, but to reduce the sandpipe pressure and the inlet flow rate. Using the established linear substitution equation, we also use this function to predict the adjacent layer RP. It can be from this two figure. This figure is established the RP substitution linear equation data, and this is the verification data. We can see from the relatives. This relatives is from 2002, 3 to 3254 to the 3269, and this interval is from 3242 to the 3254. It can be seen from the prediction result that the accuracy of the ROP model is both of the linear substitution model is both good in current formation and adjacent layers, which can meet the requirement of the site. Similarly, we established many substitution equations in other layers and verify them in the adjacent layers. In general, the established substitution equation has less loss of accuracy and higher interpretability, which can meet the interpretability requirements on the training site, greatly improve the credibility of the ROP intelligent prediction model, help to further promote the failed application of the intelligent training models. The last content is the optimization of the training parameters. In addition to the ROP prediction models, we also need to other models to characteristic the other sub-process of the drilling. For the model of string fraction and bolt hole cleanness, as there are few intelligent models in this area, and the mechanical model are relatively mature. This study established the drilling intelligent agent based on the mechanical model. And since the target well in this study is a vertical well, the impact of variable deviation on the string fraction and the bolt hole cleanness can be ignored. Based on literature research and the soft string model and the rock cutting transportation ratio were used to characterize the string state and the cutting transportation state. The input of the and the output of these two agents are shown in this table. These two tables. We use the NSGA2 algorithm to optimize the drilling parameters. According to the analysis of the input of these three agents, the common controllable parameters are WB and inlet flow rate. In addition, consider the rotary speed and sandpipe pressure also have a great impact on ROP. So the comprehensive consideration, the final controllable parameters are the WB, rotary speed, rotatory speed, sandpipe pressure, and the inlet flow rate. In the process of establishing the intelligent optimization model of drilling parameters, it's still necessary to optimize some hyperparameters of the NSGA2 algorithm. The hyperparameters that need to be optimized and the optimization range are shown in this table. Taking into account the calculation effect and the calculation effect, the optimal generation number and the offspring population number are 50 and 100 respectively. The left figure shows the change of the number of Pareto solution and the calculation time with the increase of the generation number when the offspring population number is 100. With the increase of generation number, the computing time of the NSGA2 model increase linearly. However, when the generation number is 20, the increased trend of the number of the Pareto solution is obviously slowed down. And when the generation number is 50, the number of Pareto solution basically remains unchanged. Considering the commute time and the cost of the number of Pareto solution, the optimal generation number is 50. The middle figure shows the change of the number of Pareto solutions and the calculating time with the increase of offspring population number with the generation number is 50. With the increase of the offspring population number With the increase of the offspring population number, the computing time of the ESG to model increase linear first and then slow down, and then slowly, and then linear. However, the number of parallel solution increase and then change to linearly. The right figure shows the 3D distribution of the parallel solution when the well depth is 2,300 meters. On the whole parallel solution, the distribution of the parallel solution is concentrated in the corner that the RP is higher than, and the string friction is small and the bottom hole clearness is high. The distribution of the parallel solution has a relatively obvious front line, and the existing parallel solution basically covers the front line curve, indicated that the optimization effect is good. The current optimization demand of drilling is in this study to increase the RP as much as possible under the condition of ensuring that there is no staking and the bottom hole is clean. Combining the expert experience and the literary research, when the string friction of this well is more than 20,000, it's easy to get stuck. And when the bottom hole clearness of this well is greater than 0.85, the bottom hole clearness is considered good. So any value function is established. The table shows the parallel solution of the top 10 scores when the well depth is 2,800 meters. Under the condition of ensuring string safety, the RP is increased by 200% at most. This table shows the comparison before and after of optimization of drilling parameters for some other depths. This table shows the statistic of a controllable parameter and the optimization effect before and after optimization of the whole well section for content formation. With the raw drilling, compared with the raw drilling parameter, the optimized RP increased by 24.6 on average, and the rotary speed decreased by 25, and the sand pipe pressure and inlet flow rate remaining basically unchanged. Corresponding after the optimization, the average RP is increased by 4.3 meters per hour. For GDIC formation, compared with the raw drilling parameters, the optimized RP, the optimized WP increased by 26, while the rotary speed decreased by 10.5, while the sand pipe pressure and inlet flow rate change little. After optimize the RP is increased by 4.08 meters per hour. According to the optimization result of the drilling parameter, increasing the WOB and reducing the rotary speed can effectively improve the RP in these two formations. It shows that the original WOB is too small, and the cutting teeth cannot fully penetrate into the formation, and the rotary speed is too high, and the connect time with the formation, the drilling bit connect time with the formation is too short. We can draw the conclusion that these two formations are most suitable for the drilling model of high WOB and low rotary speed. I also have other interesting research, but due to the time constraints, I will briefly describe on the other studies. The first one is the intelligent prediction of ROP under physical constraints. In fact, there are many ways to embed the drilling knowledge into the neural network, such as the data boundary knowledge and boundary condition knowledge and partial differential equation knowledge. and so on. This figure shows the corresponding partial equation that is extracted from the physical knowledge and added to the training process of the RP intelligent predictive model, so that the neural network doesn't violate the clear physical law during the prediction process. And this paper is this paper have been submitted to the SP journal, and maybe he will be published maybe next February maybe. The second content is the collaborative problem of the dream multi-agent. The method adopted is the multimodal graph learning method based on the dream knowledge and information exchange graph of dream multi-agent is constructed, and then a multi-layer graph neural network is used to realize the information interaction and dream state update during the dream training and prediction process. And this paper is also have been finished and submitted to the Journal of Expert System. And I think it will need a long time to publish. This is a paper I have published in. I have published an upcoming paper. If you have interest, you can check this magical. Please give me your valuable opinions. Thank you.
Thank you. Just wondering if anyone has any questions about the presentation from our last inside the group first.
Just not a question. I mean, this topic is definitely not in my wheelhouse. But just a comment. It was nice to see at the start of the presentation that you took some time to go through the drilling methodology, how it's done, why it's done, what kind of formations you're targeting, things like that. That's always nice to see. I notice that in a lot of these presentations, how often that's missed. You just jump right into the research without the background. So knowing that everybody in the room probably will have different backgrounds, different experience, so that helps to see. My only other comment would be is that after that, you might want to spend a little bit more time on the objectives of the research. I found that I got lost pretty quick. That's probably just me. But maybe for future presentations, just spend a little more time on the objectives. Your slide 31 was a really good slide showing kind of what the overall intent was, but it was already 31 slides in. So something looking a little more upfront, I think would be helpful. But I think overall it was a really informative presentation. Thank you.
Thank you.
Any other questions or
No.
Nothing from the group? So thanks again, Zhijun, and then that's the seminar for today, September 27th. Thanks everyone for attending.